I just want to show some fascinating patterns with Pascal's triangle, specifically when you look at it in different bases. So a quick introduction, this is what Pascal's triangle looks like. It's when you start with 1 and then you add the number going to the left and to the right, and these are the various rows of Pascal's triangle. There are various resources to learn it, but I just want to briefly just go over it here. But before we go into Pascal's triangle, I actually really want to break down what exactly is a number. So I'm going to use a sample number here of 1,234,567. We are going to break this apart so it's in its own separate digit. So what does this number exactly mean? Well, we typically use base 10. So we're saying there's 7 of 10 to the power of 0, which is 1, 6 to the 10 to the power of 1, 5 to the 10 to the power of 2, 4 to the 10 to the power of 3, and so on. So each digit represents how many ones, how many tens, how many hundreds, how many thousands, and so on. This should be straightforward. This is base 10. This is what everyone has been counting, at least that's watching this video, for most of their lives. And I'm also just going to have the sum of the number here, and that will always be in base 10. So I'm just using a number that we will always know, so that sum in the number is numbers that we can understand. So the reason I'm doing this is we can see in different bases, like base 9, this 1, 2, 3, 4, 5, 6, 7 actually represents a different number. This would represent 672,604. In base 8, 342, and you can go with base 7, base 6, and so on. As I go down, I do want to take note that although typically we carry over the numbers here, just because we're dealing with Pascal's triangle and digits typically go beyond what the bases are, we are not doing any carryover. So even though there is, for instance, 7 ones, we don't carry that over. We still treat this number as 1, 2, 3, 4, 5, 6, 7. And this sum is 24,412 in base 5. As I go further down, I even want to touch off the special examples here of there's even base 1, so that's a sum of 28, and that's pretty simple. That's essentially 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. You can even do base 0, where basically every digit represents 0, except for the very first digit, which represents 7. In this case, 0 to the 0 would be assigned the value of 1. And we can also go into the negatives. For instance, base negative 1, 1, 2, 3, 4, 5, 6, 7 would represent 4. And base negative 2 would represent 31. That's how I'm going to touch it for the bases. So, base x, 1, 2, 3, 4, 5, 6, 7, it represents some number, and we are going to play around with each x in Pascal's triangle. So I've moved the Pascal's triangle into our base system, so you'll notice that the triangle is a little bit curved. So how to read it is essentially you take every number, and then one row down, you add it 1 below and 1 to the left. So you should be able to familiarize yourself with this version of Pascal's triangle. And the reason we're doing this is you can get some fascinating insights. First off, I actually want to say that a lot of the insights we already know is actually due to Pascal's triangle in base 1. For instance, every row in Pascal's triangle adds to a power of 2. And that's when you just use each digit in the Pascal's triangle on its face value. So you get 1, 2, 4, 8, 16, 32, and so on. But we can do much more than that. We can also do base 2. And you'll notice that the sum of each row would be 1, 3, 9, 27, 81, 2, 4, 3, 7, 2, 9, and what you see on the screen. Likewise, for base 10, you'll see 1, 11, 1, 21, 1, 3, 3, 1, and so on. And curiously enough, you can see actually, at least at the start, those numbers in Pascal's triangle in itself. You see 1, then 11, then 1, 2, 1, 1, 3, 3, 1. Those are the same numbers. That's fascinating. And if you break down, why does it actually do that? Well, if we take base x, the sum of each row is actually x plus 1, and it's to the power of n being what row we're on, and we are starting with n equals 0. So the first row is technically the 0th row. And we can actually exactly see why, because what we're doing is when we're taking the number and going one row down, we're actually multiplying the term by x when we go down and to the left, and we're multiplying it by 1 when we're going straight down. So essentially for every term in the triangle, every time we go down a row, we are multiplying it by x plus 1. So that's why in base 10, you'll get the 111, 121. In base 1, you get the powers of 2. And essentially, for any base x, you're going to get powers of x plus 1. And there's just that formula there for you. I also just want to point out even just some, fancy examples. In base 0, you're actually going to get everything equaling to 1. So base, just because it's base 0, that means the sum is always 0 plus 1, and 1 to any power is 1. And that just shows here as well that this is part of the reason why we treat 0 to the 0 as value 1. And a further example, if we use base -1, you'll notice that the first row will equal 1, but then the rest of the rows will equal 0. So it's just another example of why we assign the value 0 to the power of 0 as a value of 1. Now, we can go much fancier with our bases. And I say, let's go with the Fibonacci sequence. For any of you that don't know the Fibonacci sequence, you start with number 1, and then another number 1, and then for each successive number, you take the sum of the last two numbers. So in this case, the Fibonacci sequence starts with 1, 1, 2, 3, 5, 8, 13, 21, 34, and 55. And it does go on forever. Now, what would the sum for this look like? Well, I have it over here, and it's 1, 2, 5, 13, 34, 89, 233, 610, 1,597, 4,181. These numbers might look familiar to you, because if you look closely, you'll see that this 1 belongs to that Fibonacci number, this 2 is in that Fibonacci number, that 5 is in that Fibonacci number, that 13 is that Fibonacci number, 34, and the pattern continues. It looks like we're capturing every other Fibonacci number. And that is actually the case. So when we're looking at the sum of Pascal's triangle in a base Fibonacci sequence, the sum is actually, the sum of the nth row is going to be the 2nth Fibonacci number. Now the question is, why? That's, it's a little peculiar. And there's actually an easy way to visualize this. I'm going to use 55 for an example, and I'll keep track of the sums here so we can show how this continues. So now when you look at 55, what are the two terms that we know consist of 55? Those are the previous two Fibonacci sequence numbers. So that would be 34 and 21. So I got those there, 34 and 21, which adds up to 55. Now 34 is equal to 21 and 13, and then 21 is equal to 13 and 18. So you get this 1, 2, 1, and I have the sum there to show that's 55. And then it continues on, and you'll notice that you get Pascal's triangle again. I just also highlighted here essentially the last term, so the ones, so the right side of the triangle, and we notice that it drifts forward for every row by two digits. So, what we started as 1 on the 55th, it's actually then, it starts at the 21st, number 21, then 8, and drifts. So when you backdate it, in other words, when we did it previously, every row you go down, you're actually going forward 2 Fibonacci numbers. Got this little arrow fancy to show everything, so each row drifts by 2. I also just wanted to point out that the Fibonacci sequence itself is not important that it has to start with 1, 1. You can start with any two numbers, and as long as the following terms follow the previous terms. So I just use an example of 2 and 7, and then you get 9, 16, 25, 41, 66, 107, 173, 280, and so on. So every term after 2 and 7 is just equal to the sum of the two previous terms, and we can see that the pattern follows. And this should not be a surprise, since it's due to how the sequence is defined that allows us to actually get the sum through Pascal's triangle. Now, what other fancy bases can we use? What about the factorial base? So you got 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, and so on. And if you take the sums of each row, you get this sequence, 1, 2, 5, 16, 65, and so on. Now we're going to go into a deeper dive, so I am going to jump over here to first let's analyze the sequence and see if we find anything interesting. Well, first off, we will notice that to go from 1 to 2, it's 1 times 1 plus 1. And then 2 to 5, you multiply by 2 and add 1. And then you multiply by 3 and add 1. And then you multiply by 4 and add 1. And you multiply by 5 and add 1. And then 6 and add 1, 7 and add 1. So that's fascinating that we get this pattern when we use the factorial system. To define the actual sequence for it, we just say the first number is 1, and then f at n is equal to n times the previous number plus 1. So that's one way to assign a function to this. But say we want the millionth value. Do we really want to go through a million values, a million rows to figure it out? There should be a better formula so we can just say, you know what, the millionth row will equal this number. So we are going to do a further analysis here. So we got here back Pascal's triangle, and I got the sum on the right. Now, for those of you that may know this, Pascal's triangle is actually can also be defined by the combination. So I'm going to jump here, this combination. So for anyone that is not too familiar with probability, so this is ways of essentially picking unique ways of from a set and different ways of combining them. So for instance, 0 choose 0, there's only one way to choose 0 objects from 0. And then 1 choose 0, there's only one way to choose one object, 1 choose 1, and so forth. I didn't want to get too deep of a dive into this because there's plenty of videos and resources out there to learn this. So if you don't know this, I'm sorry. I'm just not the best teacher, as you may be able to tell from this video. I just wanted to show something new that I haven't essentially been able to find any reading on, and I just thought it was interesting. So we look at the combinations here, and we're going to break it down into the actual formulas. Basically, the formula for any combination, it's n factorial divided by k factorial times n minus k factorial. So when you say n, choose k. And I've lined it up here, so you can actually see that the 0 factorials in the first row match up with the 0 factorial digit. And then the 1 factorial matches with the 1 factorial digit. And then 2 factorial, it matches on. And these are all in the divisors. And because the base, you multiply, they will cancel out. So what happens is the actual sum for each row is n factorial divided by n minus k factorial, with k going to n. And just because we canceled out the k factorial, because that's what the base is, essentially what it is saying is n factorial divided by 1 factorial, and then n factorial divided by 2 factorial, all the way up to n. And since it's going from essentially n down to 0, we can also reverse this, and we can just make it easier and just say it's a sum of n factorial over k factorial from k equals 0 to n. Now, there is an easier way to simplify this, and this actually involves e. And the actual formula for this, it's the floor of e times n factorial. I've put an example over here. So in the second column, I've got here e times n factorial. So you can see the transcendental numbers that are produced. And then I put the floor that shows that it produces an exact match, which is fascinating. Now, we can go even more complex. Let's do base x and factorial combined. So what this does is we're still going to use a factorial base, but we're also going to multiply it by x to the 0, x to the 1, x to the 2. So we're essentially combining that factorial base and the number system that we use in our everyday lives. If we use base 1 and the factorial, that just brings us back to the same sums that we got before. Base 1 and factorial is basically just the factorial base system. But if we go into, say, the base 2 factorial, we get this sum here. So 1, 3, 13, 79, 633, 6,331, and so on. So let's do a similar analysis on this. We'll know that from 1 to 3, you have to multiply by 2 and add 1. And then from 3 to 13, you have to multiply by 4 and add 1. And then you multiply by 6 and add 1. And then you multiply by 8 and add 1, and multiply by 10 and add 1, multiply by 12 and add 1, 14, 16, and 18. So essentially what we noticed is that by doing a combination, we went from 1 to 2. Instead of the increments of the multiplication going from 1, 2, 3, 4, 5, 6, 7, 8, it was going 2, 4, 6, 8, 10, 12. In other words, the increment has increased from 1 to 2. to put it into our sequence formula, f at 0 equals 1 and f at n equals 2n times the previous number plus 1. We can, we can generalize this for all of x. So for base x and factorial, we actually have the first term being 1, and then it will go x times n times the previous number plus 1. I also just wanted to use the example for 2. So if we just use the round of e and a half, when we're using different bases, the formula does get a bit more complicated. So for the base 2 n factorial combination, the actual way to predict this, if you remember before, it was e times n factorial. But now you actually get e to the exponent of a half times n factorial times x, which is a base system, to the exponent n, and n being what row we're on. So I have here on the left the actual numbers of our sequence, and then on the right I have the full transcendental number that's produced from this formula, and we can see that it rounds to the exact same number. Now, you might wonder why I use round instead of floor. In official works in the previous formula, I did find the floor function was correct. But when I've been using different x, I find that the floor function does not always work, and round seems to be the best. Although, when we're working in different bases, for instance, we're talking base 10, so it's easy to round to the nearest integer. But I have not dug into any further study to see if, say, any rounding in different bases would change anything. So in general, when we're using a factorial and base x combination, and you put Pascal's triangle on there, the formula to get the sum of each row is you round the formula of e to the exponent of 1 over x, and then you multiply that by n factorial, and multiply by x to the n, where x, again, is our base x, and n is the sum of the nth row of Pascal's triangle. I did want to do one more example that I found interesting, and this is the base -1 and factorial combination. So you can see that the sum here goes 1, 0, 1, -2, 9, 44, 265, -1,854, 14,833, and -133,496. If we put it into our formula, we can see that the round function works. This is also an example of why I like to use the round function instead of the floor function, because if we use the floor function, sometimes it rounds off to one value of 1 away from the appropriate value. But if anyone recognizes the sequence 1, 0, 1, -2, 9, -44, and so on, you might have heard of the subfactorial, which has the values 1, 0, 1, 2, 9, 44, 265, 1854, 14,833, and 133,496. For any of you that don't know, the subfactorial, it's got to do with the number of derangements in a set. So it's just fascinating that we've come about a different number, or a different way of counting subsets, by going into a negative base combined into a factorial base. There are many more examples, but I just find that Pascal's triangle is fascinating, especially looking at different bases. I'm looking for different ways of approaching this, but I tell you, the viewer, can you think of any other interesting bases that would be, interesting, and get any cool ideas that come about? Thank you, and I hope you enjoyed this video.